Assalamualaikum. My name is Muhammad Irsyad bin Muhammad Azwardi and my message number is 196.199. So today I would like to present about my poster of my final year project, which is the title of Analysis of In situ for the topographic data of fracture damage in metals from tensile test experiments. So I'm from the Department of Mechanical and Manufacturing Engineering, Faculty of Engineering, University Putra Malaysia. Right. So as for the introduction for this project, uh, this project is focuses on the ductile damage in metals. So ductile damage is a closely related to the evolution of the voids, and there are three phase mechanism in the ductile damage. First is the void duplication, which is the formation of the small cavities at the cross section. Second one is the void growth, which is the voids grow with the plastic deformation, and the last one is the void coalescence, which is the voids merge to form micro crack, and the crack continues until fracture. So in the past, the characterization of the ductile damage only focuses on the post-mortem characterization only, such as the fractography of fracture sample, and they have several limitations. So, therefore, in the recent years, there are newly tools that are developed, which is the in situ characterization using X-ray tomography, and this tool is very beneficial nowadays because of its advantages, such as it is a non-destructive test. It is can produce a body information, which is 3D plus time, and also it can produce a qualitative and quantitative analysis. So move on to the problem statement. The problem statement for this project is the TACV titanium alloy, which is largely used in the medical and aerospace industries due to its excellent mechanical properties of mechanical resistance, toughness, and ductility. However, there is a lack of understanding of the damage mechanism until fracture inside these materials. Therefore, the characterizing the damage of the material is important for the design of this material for industrial purposes. So there are two objectives in this research, which is the first one is to characterize the damage behavior inside a TSAB alloy with deformation. And the second one is to investigate the effect of the traxiality on the damage behavior of TSAB alloy with deformation. So for the methodology for this project, I just started with the in situ test of a TSCB, TS6B metal, uh, the tensor experiment, and then it will go to with the processing of the tomographic images. After that, we will obtain a raw data and images in the form of qualitative and quantitative information. And then we analyze the data to produce the graph. And last one, we can visualize raw images using the software. Right, so move on with the result and discussion. The results are divided into two parts and or the two objectives, which is the first part is the characterization of the damage behavior. Okay, so the material that used in this project is a TSCV alloy, right? So the first one, the first graph shows the mechanism measurement, which is shows the true stress strain graph of notch sample, and the true stress is determined by dividing the tensile load by the instantaneous area. Okay, so the second one is the void volume fraction. Right, the void volume fraction shows the volumic amount of damage. As you can see here, the damage seems to increase at exponential rate at around strain value of 0.2. And the figure in the box also illustrate the qualitative observation, which is a 3D views of the voids formed along the strain. So as you can see, at the strain number strain equal to 0, we can see that there are no voids nucleated or void appear inside the metal. And at the strain 0.18, there have few voids appeared, and the highest strain is 0.29. There are lot of nucleation of the voids appear inside the metal. So this is the void nucleation, which is shows the increases of the void nucleation along the deformation. And these are the example of the void coalescence, which is the two different voids will merge to form one big voids. Like, so the next part of the result is the effect of triaxiality's effect of damage behavior. So for this part, the damage behavior inside the specimen of two different geometries are being compared. The first one is smooth and the second one is the notch sample. Right, and the smooth sample have a lower initial triaxiality compared to the notch sample. Right, let's look at for the first graph for this part. So the first graph shows the true stress and two strain graph from both specimens. So the notch sample, which have a higher initial triaxiality, has a slightly higher yield stress value compared to the smooth sample. However, the ductility of the notch sample is lower compared to the smooth sample. Next is the void nucleation. Right, so the void nucleation, it shows the density of the void across the deformation for both the geometric specimen, and it also shows the increase of the void density also starts at lower strain for the not sample. Right, so the void growth, it shows the shape of the singular void. So in the notch sample, both the five largest voids grow faster compared to the smooth sample. It shows the higher triaxiality induces a higher void growth rate. And at the figure here also shows the evolution of the void shape across the deformation for notch and smooth sample. And here we can see that the void grow, and also in terms of shape, the void will grow from and forming a more spherical shape of the voids. Right. So as a for conclusion, the study of the nucleation growth and coalescence growth mechanism was successfully performed using this method. And the formation of voids is faster in notch sample and then in the smooth sample. And an increase of traxidity causes the voids to nucleate at lower strain values and the voids to grow faster. And application is in SGG. Alright, so the application in SDG, which is means the Sustainable Development Goals. This method is a non-destructive method. So this method can assure the integrity of the material used in any experiments because we can protect the specimen after the test has been done. For me, alright, so I think that's all from me. So thank you for lending your time to hear my presentation. Thank you.